All right, wait a second. Let's do this. Right. So today we're going to dig deeper into multiprocessing and multi-threading and look at a few facilities that first make our code a bit cleaner. So last time we used queues to transmit event information, like we should stop the thread or we should stop the process, or to share common objects across every process or every thread. This is not optimal for several reasons. One of these is that events should actually have their own semantic, and they shouldn't be sharing that with the workloads that we share across the workers in our ventilator worker sync platform. And that for sharing common objects, queues are not really efficient. So today we're going to see a few more tools that we can use, and then we'll spend most of the lecture analyzing the problem that we had last time with this tool. And now we have to change it so that we make it work, in particular for multiprocessing. So let's start with events. Events are simple shared flag. Basically, you can set them or clear them. There's not much else you can do, and you can monitor them across threads or processes. Other threads or processes can check the state, and this check is atomic, so you don't have to worry about any locks or anything that you're going to have to implement. And they're usually used to signal certain events. Well, the name says, right? One of these is actually checking if we should stop processing. So a typical thing that you will see in multi-threading or multiprocessing is that you create an event, you set it using the dot set, and then you do basically the main part of the process. And then once you finish doing the main part of the process, distributing your data to your workers and so on, you clear the event, right? And it gives the signal to everybody that it's over. So what you do in your worker is basically you have a loop where you have while the event is set, and there you do your job. So every time that you are back at the beginning of the loop, you check if the event is still set, and you keep going. And when the main thread or process clear the event, you stop processing. So that's a typical thing that you will see in many multiprocessing situations. So clear what the event are and what they do. I mean, it's really, really simple, right? This takes away the complexity of creating a message structure in our queues, of producing these messages, of waiting for everybody to look at them and so on. This clears up our code, right? It's not about efficiency here. It's also about efficiency, but mainly here is about separating semantically events from data messages. So second thing that we need to look into is locks. Locks are a pretty easy thing. They are used to guarantee atomicity when you access some shared resources. So, I mean, if you had done any multiprocessing in any language, you know what a lock is, but we're going through this anyway, step by step. So basically what you want to do with a lock is acquire and release it. And the lock itself guarantees that if you acquired it, you are the only one to have that lock. And when you release it, other can acquire it. The acquisition is blocking. So when you acquire a lock, if somebody else has that lock already, until it releases, your process is blocked, and it waits for that lock to be released. Once the lock is released, depending on who decided to acquire it as well, and what your multiprocessing platform wants to do with those requests, you will get the lock or somebody else will. And once it's your turn, you can acquire the lock and do your process and then release it. So why would you use that? You use it usually to protect access to certain memories. For example, if you're writing and reading from a certain array that has to be written completely before somebody can read it, because otherwise it doesn't make sense. For example, if you want to produce a transformation array for a three-dimensional transformation, a fine transformation, if you start writing the first line, and then somebody starts reading, and it has the first line of the new matrix and the next 3 lines of the old matrix, that doesn't make sense. It's not even an affine matrix, right? Because it doesn't actually comply to all the, so you cannot distract all our angles, you cannot distract anything. So you must be sure that you write it from beginning to the end before anybody reads it. right? So these are the typical things where you want to apply a lock. But this is not even the worst. The worst is actually if you produce a low-level race condition, because you're accessing the memory at the same time. So it's even worse. So basically, the point is, yeah, acquiring log blocks the process until you lock free. The point is always use a lock unless you really know what you're doing, right? For reading and writing shared info, shared memory. So how you use a lock in Python is very easy. And what I'm saying, as well as for the event, it applies to both threading and multiprocessing, right? So there is different classes that you're going to use for locks and for events, but they follow the same API. So you can share this information across your threading multiprocessing programs. So what you do, you create a lock, and then in your main, for example, one of your threads or multiprocesses, you acquire the lock. You, for example, set a shared variable to some value, and then you release the lock. And on the other side, somebody will then acquire and read the variable and then release it again, right? So this is the standard process. Before you change or before you read a shared memory, you just acquire or release it. The only really case where it makes sense not to do this is if you have a read-only information that you're sure that nobody is changing, then you can actually do it without a lock. But the moment that you actually are changing this information while other processes have access to this information, you might want to lock it both for reading as well as for writing. Any question about this? I mean, again, this is pretty basic stuff. So now it comes to something that is a bit more complex. So for managers, for multiprocessors, we need to use particular versions of events and locks. If you use a standard lock or a standard event in Python and you start a multiprocess, you will see no error. Your locks will work, your events will work, but they will not actually do anything because they live in one process and they will not share across multiple processes. So you can set an event, clear an event, and the other process will see nothing, right? The same goes for locks. You can acquire a lock and the other process can acquire the same lock because they are actually two different locks initialized in their own processes, right? So what you want to use is their synchronized version of locks and events, and they are produced by managers. So the easiest way to use this infrastructure in multiprocessing is to create a manager and to create then the specific locks events within the manager. The manager provides then these locks to all your processes. So you create them in one process and then you share it across the other processes when you instance the new processes. And this works fine. So how you do that? You basically create your manager. With the manager, you create a new lock. You can then acquire, set the variable and release it. And it works just exactly as the same thing. But when you start the process, you just pass this lock to the next process and it will work also in the next process. And the manager will take care of synchronizing the locks in the two processes. Clear? Okay. So, I mean, otherwise you can write code, it will work, will do everything, but it just won't use the lock. So you will end up with some strange bugs and you don't know why, because you use the lock, you know, you're safe, right? Actually, you're not. So the next step is how do we share memory across different processes? I mean, in threads, you don't have to do anything. You just share the variable between two threads and you can read and write from each thread. We'll see that. There is actually no need to do anything special. But when you go into multiprocessing, you have basically two strategies to do this. The first one is using a queue, sending the data over a queue and receiving the data on the other process. And this implies a certain number of operations. The first one is to take the object, marshal it, so serialize it to some streams of byte, saving into some memory that gets allocated in runtime, then sending over the reference to the other process, unmarshalling the object from memory, and then passing it actually to your code, which, as you can understand, if you have a huge array, it might take some time and it might not be the best way to do it, particularly if you have to send it across like 15 queues because of different reasons. in this case, you might want to consider, if you're moving a lot of data, you might want to consider to actually use shared memory. And shared memory is a low-level access to memory, which means that everything is in your hand, but you have to be responsible. So shared memory, what does it do? It allocates a pointer to an array of bytes that can share across processes. That's all it does, right? So you have this pointer to this piece of memory, you share it with other processes. How to read from that piece of memory, from the bytes inside, is up to each process. It's not a complete object. It's not marshaled. It's up to you to read it. What you do is that you basically initialize the objects in your main process. You put it in bytes, you save it to memory, and then from the other process, you unmarshal it into a new object, right? And this is quite efficient with several classes. For example, with an NumPy array, we'll see you can just allocate the buffer. We can just pass the buffer of where this array is saved, and the array is not really recreated. It's just putting a mask on top of the bytes that are already in memory. So you don't do much. You just create a very lightweight infrastructure. And again, cannot stress enough, you always lock when you're writing and when you're reading, unless you precisely know what you're doing. And then, but you don't want to do it because you probably are missing something of the whole picture, and you probably end up with bugs if you don't do it, right? So always use locks when you're reading and writing to share memory. So how do you actually use share memory? Let's make an example. Let's say I want to use share memory to pass this particular matrix, which is a 4x4 random matrix, right? So I create an object, 4x4 random matrix, and then I create my shared memory. Now I could have done this by just, giving the size by hand, but since I don't want to do that, I don't know, in particular what size is this? It might be implementation dependent. I don't know. Basically, what I can do is I create the object, measure its size, and then create and allocate some memory for it to be saved. Now, the memory that I've just allocated is empty. There's nothing to do with this object. So I still need to copy the object inside. All right. So to do this, the next step is I get actually a reference to this memory. So I create a mask on top of this memory by using this particular constructor in the array, for example, and I pass it the shape, the type, and where is the buffer. So where in memory is my array? And at this point, I can just copy the content of A into my shared memory reference, right? So this is a one-time operation. I have to copy the data. Of course, I could have also directly created the content here. I mean, I basically would have skipped one step of allocating this memory for this object. So if you know what you're doing, again, you can decide the size of the memory you need and then write the data directly into the memory from here, right? This is just an easier, more safe way to do it, but it's the same. So how would I then read the memory from a different process once I share this reference to other objects? Well, yes.
So when you create the shared memory, there's a size equals something. So which means you first specify the size of the shared memory.
Yes. Yes.
You cannot just put something.
No, okay. You have to decide how much you want to allocate in memory before you share with other processes.
Okay, then you need to pre-know that a size something what you want.
Exactly. So you might, that's exactly what you want to do. And then in another process, what you do is exactly the same thing that we used here. You just use an array constructor to read the object from that buffer, right? So now you have one array and p array, one NumPy array in your main process, and one NumPy array in the second process that point to the same memory. So when you change a byte in here, it will instantaneously be changed also in here, right? That's why you need a lock, because you might screw completely the format of the NumPy array if you try to write at the same time with both. And even if you just read on the second and write on the first, you might actually end up with garbage because you have starting to write some bytes and they don't make sense with the rest of what is inside the memory, right? Until you finish writing. So if you don't do this atomically, you will end up in trouble.
Daniele,
Yes.
when I use the shared memory directly from Python, I always have to use these NumPy methods to construct the low-level data type as in C. So I can only use integers, floats, whatever in arrays, in structs, but I can never use any stuff that has a pointer or reference to a Python object in it, right? So I can only use the basic data types for it.
Right. So you are not allowed to get out of this shared memory, right?
Yeah.
It's not
Okay.
your memory. I mean, you're bound to every process has its own memory allocated. So when you start reading from the shared memory with a pointer to another part, it's actually that doesn't work anymore, right? You get a memory exception.
And this square brackets, colon, square brackets notation is for a deep copy, or what does it do actually?
This is actually a matrix copy in NumPy, so you just copy the content of A into the content of sharef.
Okay.
Right. So, and this is again an example for NumPy. If you're using other type of objects, it's up to you. Are you marshal and marshal stuff from memory, or are you reference memory with the constructor? This is really dependent on what you're saving to memory. Right. So I'm using NumPy because most of the people here will probably use it from NumPy. But then again, if you're saving to bytes something else, how you actually put an object structure on top of those bytes in memory, that is dependent on what the object is.
Mm-hmm.
But the requirement here is, of course, that you are able to marshal the object into memory in a complete way, right? So no weak reference, no stuff that's lying around.
One last question. The data structure behind A, the layout in memory, is something that comes from NumPy, but will probably use maybe a more Pythonic way to organize the data. But the data structure that is behind the NP-ND array in SAHMREF, this is probably follows the C type.
No, this is the same. This is the same. So NP random rand actually is initialized just an ND array with a certain size for the content that it has. So it has exactly the same structure, it's the same object that you're creating.
Ah, okay.
That's why it works, because I basically don't create a new object. I just put an interface on top of a memory that already has all the content of my object.
Ah, so it's internally the NP libraries are, the NumPy libraries are already using the low-level C types and are very close to the C memory alignment rules probably and so on. So I can also take the same stuff and interface probably the shared memory from a C program and then access the same binary data, right?
You could, yes. And there
okay, good.
We will not look at this today because I thought I might actually want to work with shared memory instead. But there are ways to do this with Pythonic objects in managers. You can create values and lists and arrays and dictionaries, and then share it across processes using the managers, right? But actually, that works also for MPRA, but this is the preferred way to use it for MPRA. And this, since NumPy is the main goal here, when you share memory, it's probably a good idea to look in this particular example. But if you have Pythonic objects, then you might want to do it with a manager. It's easier.
Yeah. Okay. Thank you.
Any other question for share memory?
And if you use the manager.list, then you don't need the log, right? Because it's the log inside the manager.
Well, no. Whenever the manager is just there to synchronize the stuff around, but I don't need to look into the library because I didn't look into it. But I would assume that you have to lock it. Okay. But anyway, it's in the standard library documentation. It just is if it's thread safe or not. It's just one thing in the library to check. Anything else? Okay. So one thing that we will run into, and you'll see that in multiprocessing we have to take care of, is that when you create a new process, if this process is an object, so if you start the process by creating an object process first, and then writing its init, and then writing its run, and then calling start, you might end up with some exceptions like a weak graph field was a weak graph and cannot be pickled. What does that mean? It means that you have, for example, allocated some shared memory, you have saved this shared memory in the init, or you have allocated the list, the manager list, for example, and you save this in the init itself of the process. And when the process gets transferred to the new, well, the new core, the new process, new thread, whatever you want to call it, the MP process, the class, the object, right? It undergoes a certain process. I'm using process too much. It undergoes a certain workflow. Okay, the first part of it is taking this MP process object and transforming it into bytes and writing it to memory. This is the marshalling of the MP process. Then a new thread, a new operating system thread that started with fork, with spawn, or with other ways. And then this memory that you have saved your process to get unmarshaled into the new operating system thread. And when this happens, a few things happen. This object has to be pickable. We'll look next time or the time after, I still didn't decide, into what pickle does, how far it goes, but it has limitations. In particular, if you have a weak reference like memory, shared memory access, or a manager object, it might run into trouble. It might run into trouble also for nested classes or for any other as exotic thing that you might have inside this object. So it's actually not a good way to do multiprocessing. So when you have dealing with shared memory or with some more complex multiprocessing scenario, it's probably a good idea to stick to functions and to start the process by giving the target function and passing the arguments there. Because what happens then is that you are not marshalling anything across the two processes. You're just giving the function reference, which doesn't have data, doesn't have fields. And then you're passing directly the arguments to the new process. It doesn't undergo this marshalling process and it works, right? So any question about this?
You probably already mentioned it, but that's probably the pickle thing you mentioned,
yes.
Which is like serializing self-defined, like completely self-defined classes is probably then something which is exactly that you don't run into problems when you marshal your own.
Exactly. So
okay.
If you do it like this, you create an MP process in the main thread, and then you try to marshal it and put it in the new thread by using start on this process that you created and initialize in the main thread, then it will undergo pickle, and then it will undergo a lot of problems when you start trying to pickle stuff that is not pickable. That's basically the problem. If you're doing with the function and you actually do then the creation of your classes and all these complex structures that you need to use for your job in here, in the new thread, then it doesn't undergo anything. It's already in the new core. It's already running on the new OS thread, and it can do everything that it could do on the main thread without any problem. So when you transfer memory from the main process into the new process, at the moment of start, make sure that everything that you communicate is very lightweight. It doesn't have internal structure. It doesn't have complex object-oriented organization, because that could run into problem in this process. Make sense? All right. So now let's look for examples. This is the main part of today's. And right. Let's start with multi-threading, which is the easiest part. And let's look at this in detail. So first of all, I have designed a fake source from our problems. So basically, this is just generating random matrices 4x4, hundreds of them, every time I call next, right? Every time I iterate to the next object. It's just an iterator, but it's interesting to show you how you can implement iterable in your own generators without allocating the memory for 1,000 objects. You can just yield the next one every time and then read it from file or do something like that, right? So this is something that you look a lot if you're dealing with big files and you want to not allocate all of the memory just to read the file and then return them one by one, but just you want to keep reading as time goes by. All right. So what is our idea? Our idea is that we have the same ventilator worker sync as last time. The ventilator just produces data by reading from the source. And every now and then it updates our kernel, our filter that we use to multiply this data with and produce results. And when it does, every worker should update its filter and keep working then on the new data. And we want to use events, locks, to make sure that we do the right thing at the right time. And we keep the queues for the main processing of the data, right? So how do we structure this? When we start the worker, we want to pass a reference to the ventilator. I will explain why. This is actually a very important part. And then we want to have our sentinel for exiting the process, right? To signal the exit of the process. This is an event. We want to have our ventilator in sync queue like last time. And we want to share a lock, which is the update lock that the ventilator will acquire when it wants to update the filter. So, right, that the other works will not read the filter at the same time while the ventilator is writing. So, but we don't pass the filter here, we pass the ventilator itself. The reason for this is that if you are doing something of this kind in Python, A equal 1, B equal A, B equal 2, and then print A, what's the result? Is it 1 or 2? First assign 1 to A, then I assign A to B, then I assign 2 to B, and then I print A. What do I get? 2 or 1? 1. Why? I assign A to B, should have the same object now, right? They're not reference. They are evaluated objects. So the interpreter in Python first evaluates the right-hand side, and then it assigns it to the left-hand side. So if you do A equal A plus 1, that's fine because you still have the same reference. If you pass it to somebody else, it will keep being the same reference because it will just first evaluate this stuff as value and then assign it back to the same reference you had before. But if you do this, it doesn't pass the reference. It first evaluates the value of the object to the right, and then it passes to the reference on the left. So you cannot transfer reference of objects in Python easily, which means that if we want to access the filter, if we were to pass the matrix itself into the worker and save it to self matrix would be a different reference than ventilator self matrix. So if we updated the matrix on the ventilator side, it wouldn't be updated on the worker side, right? So we need to access the parent object directly and access that object, that reference inside the ventilator. I know that the ventilator is a fine one because it's just an object that I can access at every time, but I cannot access the matrix once I've located, okay? So that's why we use that. But anyway, this can cause a lot of bugs if you don't pay attention when you pass objects and actually they are different objects after you assign them to self, right? So yeah, what we do then in run is pretty easy. We have to basically run until the sentinel is cleared, right? If my sentinel gets cleared, then I am going out of the process. But until then, while sentinel is set, I can go on. But I want to make sure that I'm not running in a deadlock. So there's two things I need to check. I need to update my filter now and then when the ventilator tells me it's time to update it, and I need to monitor the queue. Right? So if I am, let's say that the filter decides to update, the ventilator decides to update the filter. And I am waiting on the queue for stuff, but the queue is empty. If I am waiting on the queue for something, but the ventilator is not producing new data because it's waiting on the lock to update the filter, then I'll end up in a deadlock because both are waiting for something to happen. So I need to do this this check in a non-locking way. So this might not be the best way to do it, but it shows the concept. What I'm doing is I'm checking, first I'm locking the update lock for the reading, and then I'm checking the queue. If the queue is empty, then I'm releasing the lock and I'm sleeping for a bit, just to give the opportunity to the ventilator to put something inside. If the queue is not empty, I'm processing. Right? Why do I want to do this? Because if the ventilator is in the process of writing into the filter, and I am processing something, for example, right here, I process self-ventilator filter time matrix. At the moment that I am processing this, I need the lock on the filter. All right. So I want to lock the process before I start doing this. That's why I'm checking. I'm acquiring the lock here and releasing it at the end. Now, if I acquire the lock when the queue is empty and the ventilator wants to update the filter, so it's not putting anything. If I acquire the lock first, the ventilator doesn't have a chance to write it in there. So that's why I want to release it in case the queue is empty and check again. Is it clear? All right. So, and then that's my job. If I find something, I just process it, put it in the sync queue and release my lock, so that I use the filter in a safe way and I'm done. Now, this is not, wait a second, this would not be optimal in a multiprocessing set because I am doing computation one at a time, right? Because I have the lock while I actually use my main math function, my main CPU sync. So this is not optimal in multiprocessing. But for multithreading, I don't care because I know that anyway I have the global interpreter lock. So it doesn't matter, right? It's just to show you what we would do. Let's say that this would be an IO bound process. Then I would actually first read the filter, copy it locally in memory, release the lock, and then do my processing without the lock, right? Question.
Okay, there's like under this while statement, there's like acquire, which means for each iteration you will acquire this lock every time.
Yes.
Do you need to do like every time you need to acquire lock, or just like in front of this while loop you just acquire it once, and then you just set a waiting for something to be awaited by another process or something?
What happens if I acquire the lock on the first worker and before the while loop? What does the second worker do? You also try to acquire it here, right? Mm-hmm. And it will wait for the first worker to release it. So it will be basically completely sequential. The first worker will do the whole while loop with the lock. And then the problem is that the ventilator will not have any chance to actually do anything because the lock is always acquired by the worker. So that's why I need to acquire it for the smallest amount of time that are really needed and then release it right away. Because only one process can have the lock, right?
At the same time.
At the same time, yes.
I have a question regarding threading and the reference copy. You said when it comes to the filter, that you cannot copying to self with the filter is a problem if you change it, boil it down, right? Mm-hmm. So why does it then work with queues? It should be like I have a manager, I have a thread class, and they share a queue. To make it with initialization, so I said the queue is like this queue, and then I communicate via this queue. Shouldn't there also be like because it isn't like with this argumentation, shouldn't it be like another queue? And
the queue is actually marshalling your object, passing it along, and unmarshalling back into the new thread or process. This might be optimized in threading. In processes, actually doing the whole thing, down to the last byte. And it's not actually a problem there because it doesn't just evaluate and pass in a reference. It completely marshals your value into bytes and passes it into
I meant like that the queue is not the same queue, more or less. The queue is not the queue that.
No, okay, all right, that's a different story. So the queue the queue is a reference object, it's just a reference object. You can just pass it along and allocate it. And that works. It works also for multiprocesses if you use the manager queue. What you cannot do is you cannot pass like a NumPy array and then or a value type like an int or something like that, and then change the reference and still think that it's pointing to the same NumPy array. It's not. All right. But it works for a queue.
Queue is already a reference.
Yes.
To take away
Yeah. It's an object with just there's an object reference inside.
Okay.
Right. But yeah, doesn't work for NumPy array. Doesn't work for ints. It doesn't work for strings. All right. So that's the basic concept about locking. There's nothing more to know about locking except that in multiprocessing you might need different lock or use it more sparingly because it's more expensive. But the point is, this is the same for multiprocessing or multithreading, no difference, right? In the semantic and in the grammar. Any question here? Move to the sync. All right. I mean, the sync is quite easy. It's not doing anything. It's just printing out stuff. And yeah, I am doing this with a timeout because I might end up with an empty queue, and I might not have to check my sentinel. Right? I check the sentinel, should go on, but the queues are empty, so I'm waiting forever because it's actually finished, but the ventilator didn't have yet a chance to clear the sentinel. So these are the kind of things you have to think about, right? So when comes first or last, what should I take care of? Because otherwise you end up with a sync waiting forever. And if you do, well, then you have to kill the process every time. So what we do is while the sentinel is set, we try to get something from the queue. If it doesn't get it, we pass. Simple as that. You want maybe to specify this to be accept multiprocessing empty, so the specific error that is actually passed by this one. But the basic point is this: just check if the queue is empty. If it's empty, wait a little bit and go back here, right? And that's it. There's nothing else to know about the sync. It just does its job. Once the sentinel is set, it just finish it cleanly and it goes. Questions here? Right, so the interesting part is the ventilator. We first need to initialize several things like buffer size, so how long should be the queue. Let's say we are processing 15,000 matrices. We don't want to load them all in the queue at once. So we want actually to load only something that is reasonable, to have some buffer for the workers to not lose time, to not waste time, but at the same time, we want to keep the memory allocation lean, right? So that's why we allocate the buffer size, and then we just give the size into the problem. So the worker count is how many workers do I start, and then every 30 problems that I put in the queue, I want to update my filters. I mean, it's just, I mean, if you have a problem of this type, you will have your own parameters that you need to manage, like how many images do I want to create, how big is the batch, and stuff like this. And this come exactly here. So you init your ventilator, you put all the stuff in, and then you start initiating your synchronization object. So you start initiating your sentinel as event, your two queues, and in the ventilator queue, you can pass a max size, which then will take care of keeping that queue of that dimension, right? But then you have to take care of not putting stuff when the queue is full. So this is up to you. So you then initialize the other queue, you initialize your update log, you initialize an empty worker array in the sync, and you're done with the initialization. In the run, what you want to do is, first of all, okay, we initialize this just a standard filter so that we don't have garbage inside, but we'll never use it. Then we set our sentinel so that our workers and sync, when they start, they not instantaneously leave. Right? We need to tell them if it's fine to run. And then we start initializing the worker. So just initialize the worker, passing along the ventilator, so self, the queues, the sentinel, and the log. And we just do it for in whatever workers count we decided to do. Now, if you didn't see this already, this underscore it's commonly used in Python to mean that we have a variable, we don't care about it, so that the editor doesn't bother us because the variable was never used. And then we initialize the sync, same way, like just in one object, so we just put it there. And then we start the sync, we start the workers. Now, it's always a good idea to start bottom to top, right? So that, you know, the bottom, we start waiting on something that is currently empty because the top will not yet start producing stuff. And it's clean to say, okay, let's start with something that is waiting on something empty. I know what's happening, and then let's move on. If you're starting top to bottom, I don't know, you might have some put with timeouts or something else that you need to take care of, right? So just a matter of preferences. And then we start the real processing. So we start our problem source, which is now, again, an iterator. So we enumerate in there, and for every time we hit a multiple of our update filter every X, right? So we do the update of the filter. And this is the important part. So when we update it, first we need to wait until the queues are empty. We want to process everything that we have in queues before we start updating the filter. Once the queues is empty, then we acquire the log and we do our update, which is simple, a self-filter equal to some value. And then we release the log. This is the writing on the filter itself. Now here I'm outputting something because we want to check then in debugging that our filter are actually the one that get used by the workers, which is always safe to do because when you're transferring stuff around in threads and processes, it's always safe to verify that it actually is there at the right time and with the right values. And then, I mean, if I'm not updating, I'm just doing while the ventilator queue is full. So if I don't have to write anything inside, just leave for a bit. Give the other processes a chance to do their job. And at the same time, I go back right away and check if the queue is still full. When it's not full, so when it's not full, I just put the new matrix inside from the iterator. I put the new matrix inside, go back and read the new one, and I keep it in memory. I'm waiting for the queue to be empty again and put it in, right? I could have here another buffer, but actually I don't need a buffer because the queue is giving me a buffer anyway. And it's nearer to the worker anyway. So it's more efficient to actually do the marshalling ahead of time, putting it already in the queue and let it stay there already marshaled so that the worker can then pull it at the right time, right? And that's it. Once I'm done, once I look through all my sources, I can clear the Sentinel. So tell everybody it's time to go. And then I just join all my processes or threads and wait for them to finish. Once that's done, it's over. It just goes out of the process and it just releases everything. So any questions on this? All right. I don't know if Alex was talking.
Battery 100%.
Alex, if you were talking, the microphone was out.
No, not talking, just listening.
Okay, I saw your name in the window. All right. So let's move to multiprocessing. Well, I mean, we can run this actually. Not a bad idea. Let me. Sorry about this. It's the standard. All right. So what's happening here? So I am updating my filter and then printing it out. And then I'm checking in the local process if the filter is correct. It is, right? So it's reading the right filter. And then it's printing the result of the multiplication. And that's doing it, it's doing it 30 times. And at some point it will update again at 30. This is the new filter, right? And I'm seeing that the new filter is actually the right one, 083, 083. While before it was 033. right? So it's actually doing the right thing, it's picking up the right filters, and it's doing the multiplications right. So that's about it for multi-threading. Let's move to multiprocessing. Now, multiprocessing is a bit more involved, and I'm going to look at it step by step. So first of all, I commented it out, but sometimes you need to actually tell the operating system what's going on and what you want to do. In this particular case, I am I have basically three possibilities here to use start method fork, start method fork server, or start method spawn. Now, fork should actually be the preferred way to do it in any POSIX compliant operating system, Linux, for example. In Mac, you might risk having problems because if you're using some of the internal libraries, in Objective-C, for example, libraries, even if you don't know that you're using them, they might not be actually thread safe. And then you might risk actually running into problems. So the best way to go around this is to have a check and start in fork server. Fork server is safe. In Windows, you're probably only using spawn. And that's about it because it doesn't have a fork. So this is actually something that sometimes you need to look into. Not always, and only for if you have a bug or if you have a serious performance problem. But beside that, the rest is similar, but we cannot work with classes. So the problem source is the same, but our worker is just a function. And it receives the same information, but it receives it directly from the function. And then it does from the function arguments, and then it does just our while loop exactly like before. So there's only one difference here, is that I am actually reading, as you see, my filter every time from memory. So I am basically putting the object on top of the buffer every time. And I am, I mean, I could have done this outside, but I just wanted to put it here for, let's say, educational reasons, so that you see it doesn't actually do anything new. It just, I reallocate this array to point at that memory, nothing else. But the point is, I am locking this here, and then I'm using it to do the computation. Is this correct?
You should lock it first, and then you create it.
Why?
Because another process will be doing the same thing to change the filter.
Right. So let's say that if I'm changing the filter, and I'm locking it to create this object and then releasing it, what happens here?
You are using another filter.
If I start changing the filter here with the ventilator while I'm trying to do this computation, am I using the old filter? Am I using the new filter? You know, any guesses from the audience at home?
Since the buffer is used, it could also be invalid, I think.
Could be invalid. Right? This code will run, will not create any problems except once every 2,000 times, and then it's going to be very hard to debug, right? So this is not safe. I actually created my lock. I read the array random. I'm doing everything by the book, releasing my lock and using it so that I can do the computation outside of the lock and be very safe. It's not safe. So you can do it if this is pretty much only read-only. Otherwise, you have actually to put the lock down here. And if you don't want to do this, you actually need to structure your lock in a different way. So there is like a master lock, so to say, for the filter writing, and then there is a cumulative lock for all the readers, so that you basically want to count up and go down with it, and have the readers, the workers, let's say, work in parallel with that information. But once once the ventilator wants to write, everybody has to release that log, and then only the ventilator can take it. And that's a structure we'll see next time, right? But for now, I wanted to just show you how actually, doing everything by the book can still lead you to a problem because you didn't take care of what's happening behind. The shared memory can be written outside of this filter definition, and this object still is allocated at that shared memory. So if somebody touches this memory, this array is instantaneously changed. Right? So the right way to do it, unless you do something else, right, is to do it here. Unfortunately. So this didn't yet solve your problem. Next time we'll see how to allocate reentrant blocks and do this properly, right? But I wanted to show you what's going on here. So next part is the sync, as easy as ever. This is not doing anything else. It's just reading it, and I removed the print because it was just creating chaos in the log. Yes.
So let's say your the variable or the files or whatever in your shared memory is very long, very large. And meanwhile, you have some writer to writing into something to change the contents of this file or the variable value. Then you have another reader to read the value at the same time. If you don't use the log thingy or some mutex thingy, so will it change so the reader will start the reading, right? And then there's something changing, and then just reading the latest information or just what?
So what happens is that you have two processes looking at the same array in memory, right? So
it's very long.
It's very large. You have a very large array, and these are the bytes. And then your writer is actually, writing here. And the writer is slow because it has to do some computation, reading from file, whatever. So it's writing here. The reader comes along and starts reading these bytes from the new object. Then it surpasses the writer and starts reading the rest from the old object.
Okay.
And then you don't know what you get. It's probably garbage, right? If you don't use a lock, you don't know what's happening here. All right. So what does the ventilator do? Now here, you have to be careful because again, shared memory, not pickable. So you cannot create an object, put it in a function. You basically pass the main parameters. I put that actually as initialization, but they could be passed at runtime if you add buffer size, worker count, and update filters right here, would be totally fine. But then you create the rest, you create it inside the project, just to be still on the safe side. So what you want to look at is that, okay, queues, we know that queues are safe. These are multiprocessing queues, so there's nothing to be afraid of. But if you're using events and locks, you might want to start using them from the manager, right? And create them in the manager, otherwise they won't work. So you create your event from the manager instance that you have instanced here. You create the logs from the same manager instance, and now you're ready to start. Right? So this was, so far it was only initialization of your environment. So we create our shared memory as we saw. We allocate the size. Where did I create it? Wait a second. No, I passed it along. I created outside, right? So the shared memory is created down here, allocated with default object, right? I pass it through the process as argument at runtime. Otherwise, I wouldn't be able to start the process. I need to pass it to the new process once it's started. And here I just read it and I allocate an array on top of it. And then I copy my content on top of it. So this is the standard way to set it up. This is completely useless because I'm going to initialize it again once I hit the first barrier, which is at 0 items, but it's just for show to show you how you initialize it. So then I stop event set. Now I could have called this Sentinel. In the process itself, in the process class, process object, there is a field called Sentinel. So it's probably not a good idea to reuse that keyword inside here. you might be tempted to write process.sentinel and then you're actually accessing something else. Okay, so that's why I call it stop event. And then you start the process. The process now, they are actually targeting a function, which is your worker function. And you're passing your init stuff through the args. Right? This is a different way to initialize the process. Otherwise, nothing else. It's just the same structure. And the same goes for my sync. Anything that does bother you with the stuff for now? It's pretty run of the mill. Okay. So then we start both processes and we go through the same stuff as before. So problem source, enumerate, and we check if the ventilator queue is empty. We acquire the lock. If the ventilator queue is empty and we are in one of these positions where we want to update the filter, we create a new object. We acquire a new pointer to the a typed pointer to our buffer, and then we copy the new object into memory, right? So that everybody has access to it, and then we release it. Now this is correct. This part works fantastically well, so it's safe. It's just the reading part. It needs to be locked as well, and we didn't lock it before, right? I mean, is this clear? We could actually put the acquire lock here, right? We will still be safe. Is this clear? Right? I mean, we don't care what's happening here. We still didn't write anything to memory. So we can prepare our data readout files, do whatever we want offline until we actually touching the first byte in the buffer. We don't need the lock. Make sense? So, and then it's the same process as before. Ventilator queue is full, then I need to wait. And if it's not full, I'm putting my data inside. Up.
So yeah, where the old like ND array was initialized, where the buffer where we got before.
This creation.
No, upwards the worker. Yeah. Okay. Yeah. Thank you. Just wanted to wasn't sure what's the old filter.
Right. So in here, if you have just one lock and you have to acquire it, you have to basically copy that data outside of that memory in a safe place spot while you have the lock, release the lock, and then use it for computation, which is, it beats the whole purpose, right? I mean, if I can do that, then I can use a queue. Because that's exactly what the queue does. It acquires the lock, it writes the memory, it gives me the handle. I need to acquire a lock on the other side when I take that from memory, marshal it again back into an object, and then release the handle again, release the lock again. That's what a queue does. So if I am actually copying my data back and forth between the buffer, the shared buffer, and a local object that I have completely ownership of, then I can use a queue. So this is still something that we need to look into now to make it safe. And that's what we'll do next time. We'll talk about reentrant locks and how to use a combination of reentrant locks to solve this problem. Any questions about stuff so far? Right. So just for the sake of the argument, if you were to produce the ventilator as a process, this shared memory would actually go into the init, and then we go into self. The same goes for the workers, and that same goes for the sync. Well, the sync doesn't use the shared memory, so for the workers. What happens is then, once you run, this shared memory, which is now in self, right, gets pickled. And when it gets pickled, it spits out. Your object has a weak ref field. It cannot be pickled. And that's it. You're stuck. right? So that's exactly why you actually go back to functional. But what you want to do, now this was a very simple example, so I didn't actually bother. What you want to do is actually pass along every shared object that is unmarshalable and every parameter that you need for initializing your environment in the new process. But then you want to reorganize your code within the function to actually use classes and objects and all the patterns that you are aware of, but you initialize them in the RAM, in the new process directly. You don't pass them along between one process and the other, right? You initialize them there. Make sense? So that's how you want to approach multiprocessing. So, and with that, if there is no question, our time is up. Okay.
Thank you very much.
Thank you.
All right. Thanks, guys.
Bye.
Yeah. See you later.
Bye.
Bye bye.